Hi everyone, welcome back to my YouTube videos. In the previous video of this playlist, I proved the strong law of large numbers. Now, before we move on with more limit theorems of this type, I'm going in this video to give you an example of application of the strong law of large number. So more precisely, let's look at the following problem. Let's assume that at each step of a game, a gambler is going to pick a number uniformly at random in the unit interval 0, 1. And let's assume that the fortune of this gambler is going to be multiplied by twice this number. So like the title of the video suggests, it turns out that this game is a fair game. I'm going to explain what we mean by a fair game. But in spite of fairness, we can use also the law of large number to prove that eventually the gambler is going to lose all her money. So first, let's prove that indeed the game is fair. And by fair here, mathematically, this means that the conditional expectation of xn plus 1 given xn is equal to xn, where xn is the fortune of the gambler at time n or at step n. So I rewrote this equation here that we need to prove. So why indeed this means that the game is fair? Well, that tells you that given that the gambler has xn dollars at time n, in average, at the next time step, she's going to still have xn dollars. So there is no variation of the amount of money, of the fortune of the gambler. So that's what we mean by fair game. It turns out that I have another playlist about martingale theory, and in this playlist you will learn that a sequence of random variable xn that satisfies this equation for all n is in fact called a martingale. So martingale is like a fair game. So now, how can we prove that indeed we have this equation? So, if you remember about properties of conditional expectation, the trick here to compute this conditional expectation is to rewrite xn plus 1 as some product, or at least in general a function of random variables that are either xn measurable or independent of xn. Everything that is xn measurable can get out of the conditional expectation. That's the case of perfect information. And everything that is independent of xn stays in the conditional expectation, but without the conditioning, that's the case of no information or no relevant information. So in this case, the first thing to do is to express xn plus 1 as a function of xn. Remember that the rules of the game is that at each time step, the gambler is going to choose a number uniformly at random in the interval 0, 1, and the fortune is multiplied by twice that number, which means that xn plus 1 is in fact equal to 2 times a uniform random variable times xn. So let's write this. Let's call ui the number chosen at step I, number chosen at random at step I. Okay, so we know that this random variable is by assumption uniform in the interval 0, 1. Okay, and according to the rules of the game, we have that xn plus 1, the fortune at time n plus 1, should be equal to whatever the fortune was at time n, that's xn, times twice that number. And so eventually we get 2un plus 1. Okay, now that's the number chosen at step n plus 1 times xn. So that's how we can express xn plus 1 using xn as a function of xn, and now we need to use also un plus 1, and now you see that obviously xn is xn measurable, but un plus 1 is the number chosen at the next time step that's completely independent of the current fortune of the gambler. So that means that indeed we were able to break down this random variable, to write this random variable as a product of a random variable independent of xn and another one that is xn measurable. So we can easily compute this expected value, and we obtain that. So expected value of xn plus 1 given xn, so equals expected value of 2 un plus 1 xn given xn. Okay, now the conditional expectation is linear, so the 2 gets out. Xn is xn measurable, so the xn gets out, so you get eventually a 2 xn. And then what's left is conditional expectation of un plus 1 given xn, but un plus 1 is independent of xn, and so that means that the conditional expectation, the best guess for the conditional expectation is just the expected value itself, so we need to multiply this by expected value of un plus 1. Okay, but now, well, it turns out that the expected value of un plus 1, because ui in general is uniform in the interval 0, 1, this is 1/2 times this 2 here that gives you a 1, and so eventually this indeed is equal to xn. So conclusion, we indeed have a fair game. The conditional expectation of xn plus 1 given xn is indeed equal to xn itself. Now, second question, find the density function of negative natural log of u, where u is a uniform random variable in the interval 0, 1. So this question is just a preliminary question, a preliminary result that we'll need to find after the limit in the strong law of large number, when we apply the strong law of large number. So first observe that because u is between 0 and 1, the natural log of u is going to be a negative number, a negative real number, and so negative that is going to be a positive number. So this random variable minus log u is in fact a positive random variable, and so to find the density function, what I'm going to do first is compute the probability that this is larger than, let's say, a positive number t, positive real number t. So first, let's look at, okay, for all t positive, let's look at the probability that minus log u is larger than t. Then you take you just do some basic algebra here to isolate u. So that's going to be obviously equal to the probability that log u is less than negative t. Then you take the exponential on both sides. That's just equal to the probability that u is less than e to the minus t. And now you can just draw a picture here to understand this probability. U is just uniform between 0 and 1. Then because t is positive, e to the minus t is indeed a number between 0 and 1. So maybe I know e to the minus t maybe is here. Okay, and then clearly the probability that u is less than e to the minus t is the probability of u being in this interval. That's exactly the length of this interval divided by the length of the full interval here. That's property of the uniform random variable. So that's just e to the minus t. So this is equal to e to the minus t. So from that we deduce that the distribution function of this random variable, that's the probability that the random variable is less or equal to t, that's just going to be equal to 1 minus e to the minus t. And so conclusion, the density function of this random variable is equal to 0 for t is equal to 0 for t negative, and for t positive that's going to be f of t equals, so the derivative with respect to t of the distribution function, so that's going to be a 1 minus e to the minus t prime for the derivative. And so if you differentiate that, you just get e to the minus t. And so conclusion from that, you see that the random variable with this density function is just the exponential random variable with parameter 1. So conclusion, we deduce that this random variable is just exponential with parameter 1. So that completes, that answers the second question. Finally, last question, study the natural log of xn over n. I remind you that xn again is the fortune of the gambler at time n. And it turns out that this quantity can be studied, the limit at least can be studied using the strong law of large number. And from this limit, we can deduce, in fact, that the fortune of the gambler converges almost surely, so with probability 1 to 0, which means that indeed, in spite of fairness of the game, the gambler eventually is going to lose all her money. So first, let's study this quantity. The idea is going to be to write xn, like we did in the first question, using the random variable ui. I remind you that ui is uniformly distributed in the interval 0, 1, and ui corresponds to the number selected at random by the gambler at step I of the game. So now, how can we express xn using those uniform random variables? Well, let's proceed like chronologically following the history of the game. The gambler starts with x0 $. Let's say we don't really know what x0 is, but it turns out that it doesn't matter. Eventually, the gambler is going to lose all her money, even if she starts playing with a lot of money. So then that's the fortune at time 0. Then to get the fortune at time 1, that's what we did in the first question. You need to multiply by 2 times the number she got at step 1. That's 2 times u1. So you multiply this by 2 u1. 2 u1, so this quantity gives you the fortune of the gambler at time 1. If you multiply this again by 2 u2, you get the fortune at time 2, and so on. And you need to stop at 2 un to get indeed the fortune of the gambler at time n. Okay, so we can write this into a more compact form. Of course, you have a product of n terms here. You have a 2 each time, so that gives you a 2 at the power n times this x0. And then the product here, I'm going to write it in a compact form, saying that it's the product for I equals 1 to n of ui. Okay, so you see that because at each step you multiply by something, eventually the fortune at time n is a product of terms. And now it turns out that the log of a product is the sum of the log. So taking the log here to study this quantity, I'm going to turn that into, in fact, a sum of logs. Okay, so let's do this and see what happens. So we look at log xn over n. So that's going to give you a log 2 at the power n over n, but log of 2 at the power n is equal to n log 2. So eventually you have a simplification. So I'm going to start with a n log 2 divided by n. Then we need to add log x0 divided by n again. So plus log x0 divided by n. And then the log of the product here is just the sum of the log. So we still have this plus 1 over n. And then log of this becomes a sum for I equals 1 to n of log ui. Okay, so now simplification, so clearly the n here disappears, so we just have a log 2. This quantity, I'm not going to change anything right now, but eventually when we take the limit when n goes to infinity, because this log of x0 is finite and fixed, after division by n and taking the limit, this term is going to go to 0. For this term, it's not clear, you have a 1 over n, but a sum of n terms. And you see that here we can indeed, to compute the limit of this term, use the strong law of large number. So what is that? Well, we know that those random variables ui are independent and identically distributed, so the log of them again are independent, identically distributed random variables. You look at the sum of n such random variables, but you divide by n, and so the law of large number tells you that this sum here should converge to the common expected value of those random variables. Now, that's here that we use the previous question. Remember that we know that negative log of ui is exponentially distributed with parameter 1. And so that would be better here to have a minus instead. So that's easy. I'm just going to put a minus here, but then minus there. And so eventually we can rewrite this expression in this way. And we indeed have minus 1 over n times the sum of n independent exponential random variable with parameter 1. And so eventually, taking the limit, we know that by the strong law of large number, that's here that I use the strong law of large number, we have almost sure convergence to, when this quantity is fixed, it's just log 2. This goes to 0 because of the n, and then we have a minus, so 1 over n times the sum of n independent identically distributed random variable by the strong law of large number that converges to the expected value, the common expected value of those random variables. I'm just going to write like minus log u, where u is a uniform random variable on the interval 0, 1. So again, from the previous question, we know that this random variable is exponential with parameter 1. And so the expected value here is just equal to 1. And so eventually the limit here is equal to log 2 minus 1. Okay? So now I don't know what log 2 is, but I know that natural log of e is equal to 1. But 2 is less than e, and so that means that this quantity is negative. Okay? So what we are able to prove is that this new sequence, this sequence of random variables here is going to converge almost surely to a negative limit. Okay? And so that tells you that even when it's divided by n, this quantity is going to converge almost surely to a number that is strictly negative. And so that means that log xn must converge to almost surely negative infinity. Okay, we can conclude this from that. So this implies like the fact that log xn over n converges almost surely to a negative limit means that log xn is going to converge almost surely to negative infinity. But saying that this converges almost surely to negative infinity, you have a log here that means that xn should converge almost surely to 0. Okay, so this implies that xn converges almost surely to 0. So indeed, we see that even if the game is fair, eventually the fortune of the gambler is going to converge to 0 with probability 1.